My friends, we're continuing on our journey of the foundations of thermodynamics so that you have a strong understanding as you build through the knowledge. And today we're going to dive deep into temperature. We're going to describe temperature and create a temperature scale. We're going to define the Zeroth Law of thermodynamics and then contrast heat and temperature, which is very important in thermodynamics. So, let's get started. How do we measure temperature? Well, way back in the day, there were many competing temperature scales, but one of the most famous ones that came out was the Fahrenheit scale in 1724 by Daniel Fahrenheit. And what he did was he decided to set 0 as the coldest temperature that he could make, which was a mixture of salt water, and then set 100, just for like easy numbers, to be the temperature of the human body. But then because there weren't calculators and computers back then, to make the math easier, he modified his scale such that the freezing point of water was 32 degrees Fahrenheit. It was pretty close to 32, but he just kind of set it to 32 for easy math, and 96 degrees Fahrenheit as the human body temperature. Then about 18 years later, I remember it very well, in 1742, Anders Celsius came out with his famous scale and tied it to the freezing and boiling points of water. So 0 degrees Celsius is the freezing point of water, 100 degrees Celsius is the boiling point of water. And then like 100 years later, Lord Kelvin came up with the absolute temperature scale. Once we knew there was an absolute temperature, he said, okay, well then that lowest point of temperature, absolute 0, should be 0. And that's what he did. But because the Celsius scale was so popular, he decided to use the same scale as Celsius, but just shifted so that the 0 point was at absolute 0 rather than the freezing point of water. So what this looks like, if we look at the freezing point of water, that's 32 degrees Fahrenheit, 0 in degrees Celsius, but then the 0 for Kelvin is at absolute 0. And the freezing point of water is 273.15, but absolute 0 in degrees Celsius is negative 273.15. If you need to calculate those, the temperature in degrees Celsius is 5/9 times the temperature in degrees Fahrenheit minus 32. If we want the temperature in Kelvin, we take the temperature in degrees Celsius and just add 273.15. Okay, now Kelvin is the SI unit, the base unit for temperature, but degrees Celsius is also SI unit. And this is the only exception where you can't use degrees Celsius for Kelvin when we need absolute temperature. That doesn't work. You could only interchange degrees Celsius and Kelvin when we want a change in temperature. How do we measure temperature? We can't just measure it directly, like we can measure the length with a ruler, that kind of thing. We got to measure something else, and then we relate it to temperature. To set up a temperature scale, what do we use to measure? Well, volume is really easy to measure. That was used back in the day. Many other things are used now, but we'll create our thermometer using volume. So what we'll do is we'll take this closed glass bulb with a liquid in it, and mercury was used back then, although now kerosene and many other liquids are also used, but it's evacuated so that there's only the mercury in here, and we'll stick this tube in something, say freezing water, and we'll just declare that the temperature of this freezing water is 0. We'll just decide that right now. And then we'll take the bulb and we'll put it in something else, say the boiling water, and the volume of the liquid will go up because the density will go down. When things get hotter, they typically expand, so the volume will go up, the height goes a little bit higher, and we're going to declare this temperature as 100 degrees Celsius. We'll just make that up. Now we'll measure this distance here, and just for easy math, let's say the height difference from 0 degrees Celsius to 100 degrees Celsius is 10 centimeters. Okay. Now, something we're going to need to assume, and this is very important, is we're assuming temperature changes linearly with height. So this is like y equals mx plus b. This isn't true exactly, but for most applications, it's kind of good enough. And at the 100 degrees temperature, we'll say t at 100 degrees equals m, which is the slope, times the height, h2, plus b. At 0 degrees Celsius, mh1 plus b, and then we'll take these two equations and we'll subtract them. So that gives us t100 minus t at 0 equals, now the b cancels out because we're subtracting, right? And then we have mh2 minus mh1, which is m times h2 minus h1 if we factor out the m. And if we solve for the m, the slope tells us how the temperature changes with the height. So that's 100, because 100 minus 0 is 100, divided by the 10 centimeters. That's the change in height. So for every rise in 10 degrees Celsius, the height goes up a centimeter. So we can now take this and we can make these gradation marks on our bulb, and then we now have created a thermometer. We could go and stick it in stuff and measure the temperature of stuff. So that's our thermodynamic scale. Now, the only reason we can do this, and we don't have to use volume, we can use resistance, there's light that's used, and there's so many different types of thermometers, but the only reason we can use something else to measure temperature is because of the Zeroth Law of thermodynamics. It's called the Zeroth Law because it was created after the first, second, and third laws were created. And what it says, quite simply, is if you have three bodies, and if body A is in thermal equilibrium with body B, so they're in contact with each other and they're in thermal equilibrium. As a result, they're at the same temperature. And if A and C are also in thermal equilibrium, as a result, they're at the same temperature, then it means that bodies B and C are also in thermal equilibrium. And as a result, they're also at the same temperature. And this justifies the use of a thermometer. So we take a thermometer, stick it in B, whatever the height is. Okay, we record that. If we take the thermometer and stick it in C, if it's at the same height, then we know B and C are in thermal equilibrium. And as a result, they're at the same temperature. Now, the Zeroth Law is so powerful, it also justifies temperature as a state property. The Zeroth Law also justifies the use of equations of state as a whole, which is super critical and foundational of thermodynamics. Now we've described temperature, we've set up a temperature scale, but we never really said what temperature is, right? And to do that, we've got to go deep inside and look at what's going on at the microscopic level. And I'm going to use a gas as an example. It could use any substance, but it's easy with the gas. And imagine we have these particles bouncing around and they're all moving with their own speed. And from something called kinetic molecular theory, there's this equation that pops out, and I've derived this in videos. You can check those out if you want to see them. But the average kinetic energy, the average translational kinetic energy, so that's the kinetic energy due to motion, kind of left, right, up, down, into and out, like X, Y, Z, that kind of motion. That kinetic energy, the average of that, of the whole system, is proportional to the temperature. So the temperature is a measure of the average translational kinetic energy. It's a measure of hot and cold, but what about heat? Right now, there's no heat because we have a hot body because the molecules are moving fast. We have a colder body because the molecules are moving cold. But heat is not present right now. Heat's a transfer of kinetic energy. If we take these two bodies and put them in contact with each other, we see that because of the collisions at the barrier, the slower moving particles start moving faster. Their kinetic energy increases. The kinetic energy of the hotter body goes down a little bit, and that transfer of kinetic energy due to this temperature difference is what heat is. That's kind of our definition of heat. Temperature is a state function. It's a property of the system, whereas heat is called a path function. It describes how we transfer energy from state 1 to state 2. So right here we have a high temperature. There's no heat, okay, because there's no energy being transferred. In the colder body, it's of a low temperature, still no heat because no energy is being transferred. Heat exists when we're transferring energy from a hot body to a cold body. Okay, so our foundations of temperature and heat, hang in there. It's really important to get this strong foundation in thermodynamics as you build your understanding throughout your course. Hopefully you won't be as confused in thermodynamics as I was the first time I went through. And good luck in your thermodynamics journey, and I'll see you in the next video. Cheers.